This is lesson 7.1. We're going to talk about polygons. So a polygon is a closed figure formed by 3 or more segments called sides. And we can name our polygons by how many sides they have. So 3 sides we would call a triangle. 4 sides we would call a quadrilateral. So 5 sides, this is where it starts to look like a polygon, is a pentagon. So the penta means 5, and the agon stands for our polygon. So 6 is hexagon. There's a few versions of 7, but we're going to use heptagon. 8, like an octopus, is an octagon. 9 is nonagon. 10, like a decade or a decimal, is a decagon. There is a name for 11, but we're going to skip it for right now. 12 is like a decagon plus 2 more. So we have do for the 2 and decagon for the 10. So dodecagon. And then any other number of sides, we're going to call the number of sides n, and we can just call it the n-gon. So 13 sides would be a 13-gon. Then we'd have a 14-gon and a 15-gon and so on. We're going to start by talking about the sum of the interior angle measures. We can break polygons down to triangles, and we know every triangle is 180 degrees, right? So a triangle that has 3 sides, there's one triangle in a triangle, and that triangle is 180 degrees. But in a quadrilateral that has 4 sides, when I draw one of the diagonals, I split it into 2 triangles. And if each of those triangles is 180 degrees, together that's 360 degrees for a quadrilateral. A pentagon, which has 5 sides, can be broken down into 3 triangles. Each of those 3 triangles is 180 degrees, so that's a total of 540 degrees. A hexagon, which has 6 sides, can be broken down into 4 triangles. Each of those triangles is 180 degrees, which means total is 720. So if we're looking for a pattern, when I had 3 sides, there was 1 triangle. When I had 4 sides, there were 2 triangles. 5 sides was 3 triangles. 6 sides was 4 triangles. There were always 2 less triangles than number of sides. So if n is the number of sides, then there's n minus 2 triangles, and every one of those triangles is 180 degrees. So our formula for the interior angles of a polygon would be in parentheses n minus 2 times the 180 for each triangle. So example 1, I want to find the sum of the interior angles. So I'm going to start by finding out how many sides I have. So n in this case is 10. We have a decagon. So when I want to do n minus 2 times 180, that's going to be 10 minus 2 times 180, which is really 8 times 180, which is 1,440 degrees. Here's one for you to try. Pause if you'd like. The answer is posted on Google Classroom. Here's the next example. So now they're telling me it's a 15-gon. So I know that n equals 15. So when I do n minus 2 in parentheses times 180, that's really going to be 13 times 180, which is 2,340 degrees. Here's another check-in for you to try. Pause it right now if you'd like. Answers on Classroom. For example 3, I have a hexagon. So I know that I'm going to do 6 minus 2 times 180, or 4 times 180 to get 720. And this is what the whole hexagon adds to. I have individual angles in here. So x plus all of those should equal the 720. So I'm going to add up 118, 111, 124, 115, and 145. and I get 613. So now when I subtract 613 from both sides, I get x is 107. So here's a check-in for you to try. Pause if you'd like. Answers posted on Google Classroom. So for example 4, we're going to work backwards now. If the sum of the measures of the interior angles of the polygon is 1980, how many sides does the polygon have? So we're going to take our formula for the sum, and we're going to put 1980 in for the sum. And I need to solve for n. So to get n alone, the easiest thing to do right now is to divide both sides by 180, because we were really multiplying 180 by n minus 2. So to get rid of it, we can divide. So now I have 11 equals n minus 2. So now I could just do plus 2 and plus 2. So n equals 13. There would be 13 sides to that polygon. Here's a check-in for you to try. Pause now if you'd like. Answers are posted online. We've learned the terms equilateral, which means that all sides are congruent, and we learned the term equiangular, which meant that all angles are congruent. In a triangle, they have to go hand in hand, but in all other polygons, it could be either one or the other, or neither, or both. So if it's both, we're actually going to use the word regular. For example 5, a home plate for a baseball field is shown. Is the polygon regular? There's no way to determine anything about the sides, but I can clearly see the angles are not. There are 3 right angles and 2 other congruent angles. So no, it is not equiangular. If it's not equiangular and equilateral, then it's no. So now they want us to find the measure of angle C. We know it's 5 sides because it's a pentagon, so the sum should be 5 minus 2 times 180, which is 540. We know each of these angles is 90, and we don't know either of these, but we know they're congruent because of the marks, so we could say they're both the same, they're both x. So this means that 2x plus 90 plus 90 plus 90, 270 is equal to 540. So we'll take away 270, 2x equals 270, we'll divide by 2, so we get the measure of angle C, or x, equals 135 degrees. If we have interior angles, we also have exterior angles. So each exterior angle is next to an interior angle, forming a linear pair. So next to the 79, if they have to add to 180, this would be 101 degrees. Next to the 40, if they have to equal 180, would be 140. And next to the 61 would be 119. So now the sum of these angles, if I add up 101, 119, and 140, I get 360. For this quadrilateral, we're going to do the same. Next to the 71 would be 109. Next to the 89 would be 91. Next to the 76 would be 104. And next to the 124 would be 56. So if I add up 109, 56, 104, and 91, I again get 360. So even though these shapes had different values for the interior angles, right? The interior angles in a triangle added to 180, the interior angles in a quadrilateral added to 360, both of them had the exterior angles the same. So based on the above information, the sum of the exterior angles of a polygon is 360, and each exterior angle in a regular polygon, we would take the sum, and if there's n number of exterior angles and they're all the same, we could divide 360 by n. So each equals that, sum equals that. For example 6, a convex hexagon has exterior angles with these given measures. What is the measure of an exterior angle at the sixth vertex? So we know that the sum needs to be 360, so that missing angle plus 34 plus 49 plus 58 plus 67 plus 75 would equal 360. So 34 plus 49 plus 58 plus 67 plus 75 is 283. And if I take that away from 360, I get my last angle would be 77 degrees. In example 7, we again have a set of angles that represent the exterior angles. Doesn't matter how many sides it has because we know it will equal 360. So this would be 5x plus, and now I'm going to add all these up. So that's 62 plus 35 plus 69 plus 41 plus 58 to 65. When I take that away from 360, we get 5x equals 95. And now when we divide by 5, we get x is 19. Here's one for you to check in. Pause if you'd like. The answer is posted on Classroom. For example 8, what is the measure of each exterior angle of a regular hexagon? So a hexagon, n is 8, and we learned that each was equal to 360 over n. So we'll do 360 over 8, and we get 45 degrees. So here's one for you to try. You can pause if you'd like. Answer is posted on Google Classroom. And for our final example, we have a trampoline shown shaped like a regular dodecagon, which means n equals 12. So we want to find the measure of each exterior angle. That would be 360 over n. So 360 over 12 is 30 degrees. Now they want us to find the measure of each interior angle. If I know that each exterior angle is 30 degrees, and it has to make a linear pair with my interior angle, then 180 minus that 30 would be 150 degrees. We could also have taken the sum of the interior angles for a dodecagon and divided that by 12. We'd still get 150, but it's probably easier to just take that away from the 30, or take the 30 away from the 180. And that is it for section 7.1, polygons and their angles.